It is a pleasure for me to introduce to you an old friend and a very big personality in polymer chemistry from France, Professor Jacques DESBRIERES. He is graduated from National School of Chemistry in Paris in 1978, and 2 years later he got the doctor engineer degree at Grenoble University. Today he is emeritus professor of at University of Pau and Pays d'Adour in the Institute of Analytical Sciences and Physical Chemistry of Materials and Environment. After a position of research engineer in Dowell Schlumberger related to the application of polymer in oil well operation, he joined Grenoble University in 1990 and then the Université of Pau and Pays d'Adour in 2004. His research domain is concentrated on chemical modification of natural polymer and the relation between their chemical structure, functional properties, and their applications. In the last year, his research activity were dedicated to physical chemistry of polysaccharide solutions and polysaccharide surfactant interaction, hydrogel, and particularly their characterization and their specific application, biomedical or cosmetic application, wastewater treatment, and new green processes applied to biosourced materials, microwave irradiation as an example. He authored around 200 publications, 27 book chapters, and 10 patents. He is the member of advisory board of very important journal, cellulose chemistry and technology and carbohydrate polymers, and has teaching activities in physical chemistry and polymer science. In 2009, he was appointed Doctor Honoris Causa at the Technical University, Gheorghe Asachi Iași, for his input in natural polymer science. I would add that he is one of the big friends of Romanian people. He participated many times in Franco-Romanian colloque on polymers, and he received a lot of master and PhD students in stages in France with good results. He was also a member in various jury of thesis here in Romania. Jacques, je t'en prie.
No problem. Thank you, Andrei, for your kind introduction. And I want to thank the organizing committee to give me the opportunity to present some results. And it's a great honor for me to present this opening conference. And every time I come in Romania, it's a great pleasure because year after year, many colleagues I met for the first time a few years ago become more and more very strong friends, and especially Andrei and other ones. Thanks for all the welcome, and when we arrive in Romania, we are more and more at home. I am going first today to present some results on using the microwaves for biosource macromolecules. After an introduction on microwaves, I am going to focus the results on two topics. First, the chemical modification of polysaccharides, and then the use of microwaves to extract biosource macromolecules. The first question is, have the microwaves an interest for the scientific community? And if we consider the number of published of published articles, we have observed a very strong increase during the 25 last years in the number of published articles. And especially we have 3 deadlines. In 1986, when we observed the first use of microwaves in relation with chemical synthesis. Then in 93 for the radical polymerization, and last, the polysaccharide modification in 98. And if we consider the polysaccharides, or more generally the biosource macromolecules, we observe also a very sharp increase in the number of published articles during the 20 last years. Now, what are microwaves and what are the, how they work with our biosource molecules? First, the microwaves comprise electromagnetic radiation with a frequency between 300 megahertz and 300 gigahertz. The microwaves apparatus operates at 2.45 gigahertz, and that allows the microwaves to penetrate within matter at a depth of around the wavelength, that means between 10 and 20 centimeters. By applying Planck equation, the energy involved within the microwave matter interactions is around 10⁻⁵ electron volts, which is much smaller than the bromine motion, the hydrogen interaction, and obviously the chemical bond. That means that microwaves by themselves are not responsible for chemical activation we observe. That means how they work. In fact, when the polar molecules are exposed to microwaves, they tend to align themselves with the electrical component of the microwaves. This, I have a small when this electrical field inverts at a rate of 2.45 10⁻⁹ cycles per second, and as a consequence, in the polar medium, in the reaction medium, the polar molecules are not failed to align by themselves at a rate as fast as the electrical fields. That means, due to the presence of other molecules in the reaction media, we are going to observe friction and, as a consequence, heating. To demonstrate this, when we apply the microwave irradiation to different solvents with different dielectric constant, the larger the dielectric constant, the larger the temperature at which which is reached by the medium. As a consequence, the microwaves are efficient in polar medium and with reaction involving polar molecules. That's very important if we want to consider the different reactions, to keep in mind these two parameters. The first topic will be devoted to this chemical modification on polysaccharides. And I have chosen 2 types of reaction. The first one from Lubivic's team concerns the esterification of starch in presence of lipases, which are biocatalysts, very efficient in esterification, trans-esterification of hydrolysis of macromolecules. they have compared the efficiency between conventional heating and microwave irradiation, and they have also compared two different solvents, DMF and DMSO. And when we consider the degree of substitution, whatever the conditions, they have observed better degree of substitution when microwaves are used. And whatever the conditions, we have better degree of substitution when they compare the microwave irradiation compared with the conventional heating. And we observe also a sharp decrease in the reaction time. But the microwave irradiation does not explain all the results. But for example, if we compare the dimethylformamide and dimethyl sulfoxide within the same conditions, we observe with dimethylformamide, even with a lower dielectric constant, we obtain better, larger degree of substitution. That may be explained very easily due to the fact that dimethylformamide is a very efficient solvent for lipase-mediated reactions. And second, the dimethyl sulfoxide is a very good solvent for starch. And in these conditions, the viscosity of the reaction medium will be larger, decreasing the diffusion of the reagents and decreasing the kinetics of reaction. And if we consider the products which are obtained, when they use microwaves, they do not observe any hydrolysis of starch, and the molar mass distribution is not affected compared with the molar mass distribution, which is much more effective when they use conventional heating. The second reaction I want to discuss is the chemical modification of chitosan. Chitosan is the most common derivative from chitin, obtained by deacetylation of chitin, which is the second most important polymer at the surface of Earth. The chitosan presents very interesting properties. It is non-toxic, it is biodegradable and biocompatible, and due to the presence of the amino group, it is one of the only biosource macromolecule with possible to have a polycationic nature. And due to the presence of the amino group, it is possible to carry out some specific reaction. And I have chosen one of the reactions we have performed in our group. That means the reductive amination, which allows to, by a reaction between carboxylic carbonyl group of aldehyde with the amino group of chitosan, to graft alkyl chains, allowing to have hydrophobic groups which are grafted on the hydrophilic backbone, leading to amphiphilic polysaccharides. These polysaccharides, these modified polysaccharides, have very specific rheological as well as interfacial properties, leading to the interest in using them in very wide applications. When we have compared the interest in using microwaves irradiation compared with conventional heating, and for this, we have chosen a specific mode in which we have temperature and power controls, allowing to have a very good control of the reaction conditions and the good reproducibility of the products. And here we have compared the degree of substitution which is obtained compared with the targeted degree of substitution, and whatever the conditions, that means whatever the molar mass of the chitosan sample, whatever the temperature, the targeted degree of substitution, we obtain a better yield with microwaves in blue compared with the conventional heating in brown. And in certain conditions, we may have 30% increase in the yield. And in any case, we do not observe, when we proceed with microwaves, we do not observe any polymer degradation nor deacetylation. That means we keep the chemical structure and the physicochemical properties of the polymer. But now it is very important to know if the final products keep very interesting properties and more or less the same or better properties compared with the conventional products. When we have hydrophobic groups, we are going to be able to have some hydrophobic interactions, and consequently, we observe what is called auto-associative behavior, leading with an increase in the rheological performance of the product or the solutions. Here we have measured the viscosity of different solutions, the chitosan, which is the precursor, and when we increase the hydrophobicity by increasing the length of the alkyl chain, we increase the hydrophobic interaction, the auto-associative character, and the viscosity. And as the hydrophobic interactions are favored by temperature, we have also studied the effect of temperature on the viscosity of such solution. And we observe that we may have some solution with increasing temperature, with increasing viscosity with temperature, or to keep exactly the same viscosity compared with, for example, the precursor solution. But if you consider the concentration, we may have the same initial concentration, and we keep a constant viscosity, even with a concentration which is 10 times less than the precursor polymer. And as it is an amphiphilic polymer, we expect to have interfacial properties, which is the case. With chitosan, we do not have more interface activity, even if we have some N-acetyl groups. But when we increase the hydrophobicity by increasing, in this case, the degree of substitution with the same type of alkyl chain, we increase the kinetics in decreasing the interface in the surface tension, and we decrease the surface tension, which are the symbol of interfacial properties. If we want to summarize the interest of microwaves for grafting on polysaccharides, here we have the characteristic, the conventional method, and here the characteristic using microwaves, and we increase, we have better reaction temperatures, better efficiency of the reaction, and finally, we have better results, better properties for the final products. The second topic concerns the extraction of biosource macromolecules. And I present some results on surfactants and specific surfactants. When we consider the synthetic surfactants, due to their foaming, emulsifying, antiseptic properties, we may use them in very wide applications. But synthetic surfactants are within a list of water contaminants and pollutants. And among them, the ethoxylated non-inflammable are now considered as endocrinian perturbators and they have some severe harmful consequences on aquatic medium. That means due to the problem of toxicity, ecotoxicity, environmental criteria, we have a very strong increase in the development of biosurfactants. And now we have more or less 120 kilotons, which are used each year. And we have studied saponins. Saponins are generated from the pericarp of soap nuts, and they are known to be biosource surfactants with very interesting tensioactive and fungal properties, leading them to be used in very various formulations, such as vaccines, food supplements, and health products. Their structure is here. There are some terpenoid glucoside with a glycone part, and we have a carboxylate group. The usual process to obtain such saponins is composed of first grinding step, followed by an extraction step with alcohol at high temperature and during a long time. Our strategy was from the pericarp of the soap nuts. We first have a grinding step to obtain a powder with particles smaller than 1 micron. We disperse this powder within water, and we place this dispersion in an apparatus, in a microwave apparatus, around 5 grams of such powder in 100 millimeters of water. And this apparatus has an open reflux column. And after cooling at a room temperature, we obtain a yellowish liquid extract. And after only filtration, without any further purification step, we may use this liquid extract. And we have obtained a recovery of 90% compared with conventional process, recovery of 70%, more or less. As it is a surfactant, the first property we test was the interfacial properties. And we obtain here a very small critical micellar concentration at more or less 0.1%. The interfacial behavior does not depend upon the ionic strength, and whatever the pH, the final surface tension is the same. That means it's possible to assimilate such saponins as non-ionic surfactants, even if we have carboxylic groups. And in fact, these carboxylic groups are within at the inner part of the micelle without any contact with the aqueous medium. And we have also observed a very, very small second critical micellar concentration within very drastic reaction of experimental conditions. For example, we wait for 24 hours equilibrium, and it is explained by the interactions of this surfactant with amphiphilic polysaccharide extracted simultaneously with the surfactant. We know that one of very important process to perform polymerization is emulsion polymerization. And we try to know if such saponin extracted with microwaves is able to proceed with an emulsion polymerization process. And we have carried out the emulsion polymerization of styrene within very usual conditions, the temperature of 70 centigrade degrees, ammonium persulfate as initiator, and a monomer content of 20%. And when we carry out such polymerization process, the size of the particles and the size distribution depends upon the nature and the concentration of the surfactant. And when we compare the saponins with non-ionic surfactant and another ionic surfactant, which is sodium dodecyl sulfate, we observe with saponin it is possible to adjust the size of the particles with the concentration of the surfactant, and we have more or less exactly the same size compared with a non-phenol non-ionic surfactants. With sodium dodecyl sulfate, we have smaller size, but it is very well known, and it is one of the properties of the ionic surfactants. We have spherical particles, and the size distribution is very narrow, and it is narrower than what may be observed with other non-ionic surfactants. The latex which is obtained with saponin as surfactant for emulsion polymerization is stable. We do not observe any influence of temperature nor the ionic strengths. Finally, as the saponin has antibacterial effect, we try to see if the latex prepared with such surfactant presents exactly the same property, and we carry out these experiments with butyl acrylate latex, and effectively, when we have a saponin, increasing the concentration of saponin in the polymerization process, we observe that an improvement of the antibacterial effect. We have now to work more deep in this domain, because we may improve this property, and we may have some better latex. To conclude, the microwaves answers an increasing demand in eco-friendly greener processes by decreasing the number of steps, by decreasing the reaction time, the consumption is in energy, and for us, the most interesting for using microwaves is within continuous processes with small residence time around a few seconds, 1 minute, and for extraction process. And in any case, we have observed that the final products have similar properties and sometimes better ones. But due to the high investment cost for the large microwaves apparatus, and also if we want to have some industrial process, there is a high necessity to modify already used equipment. We consider that now the industrial implementation will be limited to fine chemistry, either the use of chemical with high added value or the extraction of high added value, biosource macromolecules. In any case, now the chemical industry is faced to very important mutation due to economical, environmental, societal considerations. But in any case, we are convinced that the microwaves will have an increasing place within this process, either chemical modification, synthesis, or extraction. I want to acknowledge people with whom I have worked on this topic, and all of you for your presence on site and on video. And I do not have a lot of words in Romanian, but I appreciate to have one which is mulțumesc.
Thank you very much. If we have just one question and then the other question in during the coffee break. Mr. Parachiu, it was the first.
Thank you for your presentation. Basically, I'm engineering electronics, but I work also for chemical sensors. My question is, you use an ICM band 2.45 gigahertz. Do you use another frequency band? Maybe, no? Okay. Yes, I know. Yes.
With the radio.
Yes, I know. But maybe we discuss later. I have some reason. Maybe we could discuss directly.
But we have only used industrial apparatus.
Yes. Thank you so much. And maybe we could discuss later about.
Okay.
First question refers to the use of intensive process in chemical industry. I use, as example, ultrasound and the microwave to produce the process intensification. And my question is, if you want to develop a process of high capacity, you can use microwave and the ultrasound because this method works with small volumes.
Yes, but the problem is, in any case, it would be necessary to have very small reactors because
the production capacity, because
because it is
the production capacity.
Yeah, but we have a penetration length, and
okay,
it is not possible to have a reactor with a very large size.
The second question refers to the Kitosan solution. The evolution of viscosity of solution with which temperature we have decrease of for all solution, and you have the cases when the viscosity increase with the temperature. Can you explain more this problem?
It is due to the properties of the hydrophobic interactions. These hydrophobic incompatibility, there is no compatibility between oil and water. That means all the oil molecules are together, and the interactions between them is hydrophobic interactions. And these hydrophobic interactions are favored with temperature. We have an increase in the strength of such hydrophobic interactions up to a temperature of 70, 80 centigrade degrees.
Thank you. It's okay.
It's not a question, it's an invitation. Here at this flow, we have an flow reaction chemistry system. This is a solution. We could be able in a flow and also in a micro flow system to get high yield, high production, and to keep the low space that we need for microwave, for ultrasound, for laser, or for other physical means to intensify the process. And during the coffee break, if you like it, I could show you the system which we acquired a couple of years ago. Thank you very much.
It will be a pleasure. Thanks.